Hi, and welcome back. We are with Allen High School, and this is Pre-AP Chemistry. And we're going to move into some other types of calculations. We've done a lot of dimensional analysis, and we're certainly not going to forget about that, but we're going to incorporate some other calculations in here. And the first one we're going to look at is percent composition. And when we talk about percent composition, I can spell I-O-N, it's by mass. Now later on we can talk about percent compositions in other units, and science will, but we're talking about pure substances. Now there is a law called the law of constant composition. And that law of constant composition states that, for example, we're going to do this in just a minute. You'll see where I get the number from. But if we have potassium carbonate, that law says that if I have 1 gram of potassium carbonate, it is 56.58% potassium by mass. All right? If I have 32.9 grams of calcium carbonate, it is 56.58% potassium by mass. In other words, this is, and this is a word we used a long time ago, this is an intensive property. It doesn't matter how much I start with, the percent of potassium will always stay the same, assuming that it's pure. And that's what the law of constant composition says, that as a composition by mass, we have a constant percentage of each element. Now, a percent is equal to the part over the whole. Now, you will either be specified what part, or you'll have to do every substance. And since it's a percent, it's times 100. Now, remember, this is intensive. So what we are going to assume when we do this is we're going to assume we have 1 mole of our substance. So if we have 1 mole of our potassium carbonate, then our grams are simply equal to our molar mass. And that's going to be our whole. So let's take a look at the first part. We want the percent potassium. So you get potassium's +1, carbonates -2. So there's our formula. And of the whole, we want to find out what part is contributed by the potassium. So if we assume 1 mole, we've got 2 potassiums, and they each contribute 39.10 grams. I have 1 carbon that contributes 12.01 gram, and I have 3 oxygens that contribute 16 grams. Now, that's times 100 because it's a percent. Now, the part that was potassium was the 2 potassiums times the 39.10 grams. And if we did that math, you'll get that number I used in my example, 56.58% potassium. We assumed 1 mole, so the mass of the whole is equivalent to the molar mass. Now I'm going to calculate that really quickly here for you. I don't happen to have it on my page, just so we can use it. Well, let me just write it out. It'll take a minute, but I think it'll be worth it in the long run. All right. What is the percent carbon? Well, I have 1 carbon. It contributes 12.01. So I have that many grams of carbon per my whole, which is, again, all I'm doing right here is calculating a molar mass, right? 2 potassiums, 1 carbon, plus 3 oxygens from the periodic table. Molar mass times 100. And that is equal to 8.69%. Now, the sum of all percents has to equal 100. if we're talking about a pure substance. So to find my percent oxygen, I have two ways. I could set up a similar type of calculation to this, or for my last one, I could say that 100 minus my potassium plus my carbon has to equal my oxygen, because oxygen, potassium, and carbon has to equal 100. And when we do that, my percent oxygen would be 34.73%. Okay? Or what we could do is the same type of calculation, my percent oxygen. I have 3 oxygens, they each contribute 16. I'm assuming a mole, so my whole is still the molar mass. You wouldn't have to work it out every time like this, right? You could do the calculation real quick. But I wanted to really emphasize that what goes in the numerator, okay, if it's percent potassium, the potassium contribution goes in the numerator. If it's the percent carbon, the carbon part goes in the numerator. And if it's the percent oxygen, the oxygen component goes in the numerator. All right, let's try another one of these. Another couple of these in this video. This time, we were only asked for the calcium. It doesn't ask us for the phosphide, although it would be pretty easy to get it. Calcium is +2, phosphide is -3. So calcium phosphide is Ca3P2. Now, if you don't know how to do that, boy, we're really at the point where tutoring, help session. There's 6 teachers waiting with bated breath for you to come in and ask questions so we can help you. All right, so the percent calcium, we're going to assume a mole. So if I assume 1 mole, then the denominator is simply 3 calciums, each contribute 40.08, plus 2 phosphoruses that each contribute 30.97. Now those 2 numbers were taken directly from the periodic table. All right. Now the part that is calcium was the 3 times the 40.08. Right? And since it's a percent, we're going to multiply that by 100. Now, I want to talk about something very quickly before we move on to our next one. In a little while, we're going to use this part of it as a conversion factor. I know it looks like a complicated conversion factor, but it's really not too bad. What this conversion factor tells me is, and I don't have the numbers handy, so I got to calculate 30 times 40.08. This tells me I have 120.24 grams of calcium, equivalent to, and now I'm going to put 2 times 30.97, double check my algebra if you would please here, 182.18 grams of calcium phosphide. So we're going to use this as a mass to mass within ratio. So it's a very, very handy conversion factor as well as important in and of itself. Now, that final answer, once we crank through that math, is that it is 66.00% calcium. And it didn't ask for the percent phosphide, but all you would have to do is take 100 minus the 66, and it should be 34% phosphorus if it had asked. It didn't. Bonus information just because I love you. Okay, let's do another one. Let's do 1 more percent, and then in the next video, we'll use this as our mass to mass ratio. So we want to know our percent oxygen, better color for you here, and we have barium chlorate. We saw this earlier. Chlorate's -1, barium's +2. Go ahead and put that above there as needed. 0.6 waters. Okay, so my percent oxygen is that contributed by oxygen. So each oxygen contributes a mass of 16. Now I have 6 oxygens from here plus another 6 oxygens from the hydrate. So I actually have 12 oxygens contributing to the mass of that whole molecule. And it's got a big denominator here. Now for the denominator, I have 1 barium. It's 137.33 from the periodic table, plus 2 chlorines, right? 2, that distributes in the parentheses. 2 chlorines at 35.45 grams per mole. Now, I'm going to do this separately. It doesn't matter. Well, I'll keep it together. It'll make more sense. I have 12 oxygens times 16. And then I have 12 hydrogens. You could have just counted the water separately. It's up to you. 1.01. Wow, I thought I was giving myself plenty of line there, and I ran out of line. And then it's times 100. So this is simply the molar mass of my barium chlorate hexahydrate, and this is what oxygen contributes to that molar mass. And if we did that math, you're going to get 62.08% oxygen. So you may be asked for one element in a substance, or you may be asked for the percentage of each and every element in the substance. Now, in the next video, we will be using this as a conversion factor. So until then, this is signing off.